Hello, Chem 105 students, and welcome to the first of two lectures this week about the driving forces behind chemical reactions and the kinetics, or the speed at which they occur. In this first lecture, we're going to talk about the heat energy associated with reactions and whether there is heat that comes out when the reaction occurs or whether heat goes in when the reaction occurs. And we're going to have these terms exothermic and endothermic to describe that. We're also going to talk about a concept called entropy, or also referred to sometimes as a measure of disorder. Um, Things normally tend towards disorder in the universe. Anyone who's had a bedroom that they haven't put some energy into cleaning in a while is familiar with this idea. But it goes a little bit deeper than that and is related to chemistry, so we'll talk about that. And also, we'll talk about the factors that affect how quickly reactions go, that affect the rates of these reactions. Okay. So first of all, let's talk about the energy associated with reactions. So in some reactions, when they occur, let's say you're burning a fire in front of you. When that fire burns, you can feel that there is energy, heat energy coming out of it. And that is because burning is an exothermic reaction. Heat is released when this reaction occurs. And so the reaction feels hot to you because there's heat coming out when the reaction occurs. You could also say heat is exiting the reaction, which is the way that I remember exothermic. It's like exit. Heat is being released by this reaction. It's coming out of the reaction. It's exiting the reaction. So it's exothermic. Whereas some reactions, not too many, but there are some reactions or some physical processes as well where energy goes in. There are not very many chemical reactions that you're probably familiar with, except for maybe a cold pack. If you ever had a cold pack where you break something inside and then the cold pack feels cold, and then you can put it on your arm or whatever sore to reduce that soreness. That occurs because there's a chemical reaction that is endothermic occurring inside that cold pack, and energy has to go into that reaction in order for this reaction to go. So when you hold something that like the cold pack in which this reaction is occurring, it feels cold to your hand because the heat energy is coming from your hand and going into the reaction. And so since the energy is going into the reaction, we call this endothermic, and I think of N as sounding like in. So when I say N, it sounds like in, so that reminds me that energy going into the reaction is called endothermic. You would say that the reaction is endothermic when energy is going into the reaction. It feels cold. Whereas when heat energy is exiting the reaction, we call it exothermic. Now, these also apply to physical processes. For example, if you want to boil water at room temperature, you're going to have to put energy in. So when you boil water, you put the water on the stove, right? And you turn on the stove, and energy comes out of the burning reaction, which is exothermic, and it goes into the water to boil it. So the boiling of the water at room temperature is endothermic. You have to put energy in order for the boiling to occur. Whereas uh, also, think about melting ice. If you put ice in your hand, it will melt at room temperature, and that ice will feel cold. That is also endothermic. So when you put the block of ice, the cube of ice in your hand, it feels cold because the energy is going from your hand into the ice to melt it. So melting ice is endothermic. Boiling water, though, is also endothermic. Okay, the energy has to go in. So that's where sometimes people get confused with this feels hot idea. So the burning of the gas in your stove, that feels hot because the burning of the gas is exothermic. Now, for the water to boil, though, you have to put energy in. So the boiling of the water itself is endothermic. So be careful with this. This is just kind of feels hot, feels cold is kind of like a guide rule of thumb, like for a reaction. But for example, to boil water, you've got to get it hot. But the water is going the energy is going into the water to boil it. So the boiling of the water is endothermic, even though that happens at a high temperature. Energy has to go in. So exothermic, heat energy coming out. Endothermic, heat energy going in. Endothermic, in. Now, the natural direction, or the most common direction of change in chemical reactions, is exothermic, for reasons we'll talk about briefly. But most reactions you're familiar with, burning things, or sometimes when you mix something, energy will be released. And that is because the natural direction of most chemical reactions is the exothermic direction. Um, Endothermic reactions won't go spontaneously. They won't be spontaneous. So I'm going to introduce this word, spontaneous, right? Uh, my pen, spontaneous. And this is a word your book uses. A reaction will only be spontaneous, an endothermic reaction will only be spontaneous if there is favorable entropy, spontaneous. And so we use the word spontaneous to mean that a reaction will go all on its own. You don't need to put energy in to make it happen. Similar to the way a ball will roll down a hill on its own. You don't need to put any energy in for that to occur. That's the natural direction of a ball rolling down a hill, not up a hill. If you want it to go up the hill, you've got to put energy in, right? And so when it comes to endothermic reactions where you're putting energy in, they won't go on their own unless entropy is favorable. So entropy is a word that describes the measurement of disorder. So let's go a little bit more into entropy. So entropy means disorder, and it means disorder in molecules, so or in arrangements of molecules. So, for example, when a liquid or solid boils to a gas, those gas molecules or gas atoms will have a greater disorder because when a substance, or like let's say a liquid like water, when it is in the pot before you boil it, all the water molecules are right there. They're not very spread out. They're pretty orderly. They all sit on the bottom of the pan. They're even more orderly if they're in a solid form and the molecules can't move around very much. Uh, but when you boil the water, those gas molecules can literally go anywhere. If you boil water now, some of that water will end up halfway around the world a month from now. And so there's a lot more disorder when molecules are in the gas state than when they're in liquid or solid, because they can fly literally anywhere, as long as they're not in an enclosed container. Entropy also increases when large molecules break into smaller molecules. So if you have, one molecule here, let's say these two are stuck together, and then a reaction occurs and they break, and there's one over here and there's one now over here. So these two pieces have greater disorder because instead of being locked together and always in the same arrangement, now you can have one piece over here and another piece over here, and so they have a lot more possibilities for being arranged, and that's a lot more disorder. Entropy also increases when pure substances are mixed together, or when just pieces of things are mixed together. So for example, I always like to use cards, or your book has a picture of a jar with jelly beans in it, and the one where all the jelly beans are mixed, that's more disordered. And then it has another picture where there's jelly beans here, there's jelly beans on the top, which are the red ones, and there's jelly beans on the bottom, which are the yellow ones, and they're all separated. And that's less disordered. So this is lower entropy. Whereas if they're all mixed up, that's greater entropy. You can think about it this way: that if you mixed up, if you mixed up like sugar and water, it's kind of hard to separate them, right? Or even if you mix up the jelly beans. Now, in order to get them so that all the red ones will be on top and all the yellow ones will be on the bottom after you've mixed them, you've got a lot of work to do. You have to fight the entropy. So, in general, things always move towards greater disorder. And that is called the second law of thermodynamics, and that is an important law in the universe. And you may be thinking, well, what about very orderly things? How do orderly things exist then? And orderly things exist only because energy is constantly fed into them or put into them to keep them orderly. For example, your body is a very orderly arrangement. But if you were to stop eating for too long, you would die and your body would become very disordered very soon after that. So, this orderliness is kept, things are kept orderly. Entropy is fought. You have lesser entropy only if energy is fed in along the way to fight that entropy. And so that's why we say, like on the last slide, reaction, the natural change of reactions is exothermic, releasing energy. And the reason why that is because that causes all the molecules around to be hotter and they'll move faster and thus they'll be more disordered. So also you have greater entropy when you have a higher temperatures. The molecules are just moving around faster and they're more disorderly. And so exothermic reactions increase the entropy around the exothermic reaction because it makes all the molecules hotter and they're moving around faster. And so that's why the natural direction of reactions is exothermic. But you can have endothermic reactions if entropy is increasing somewhere else at the same time. Just like you can have a very orderly body with low in entropy as long as you're constantly feeding it food which can release energy into your body via an exothermic reaction. So the natural direction of change is towards more disorder, and that can be in the form of exothermic reaction, increasing the temperature, or it can be in the three different ways that we just discussed here, forming more gases, larger molecules breaking up into smaller ones, or pure substances being mixed together. Okay, I used an example of your room. Another example will be a brick wall will eventually fall apart over time, but it will never assemble. The bricks will never assemble themselves into a brick wall because the natural direction of change in the universe is towards greater and greater entropy. Okay. Uh, and so that describes whether a reaction will occur or not. A reaction is more likely to occur when you have exothermic reaction with increasing entropy. Uh, if you have an endothermic reaction with decreasing entropy, that is never going to go. If you have an exothermic reaction with increasing entropy, that will always go. But if the reaction is endothermic, then you're going to need a lot of entropy change to make it occur. And if you have a reaction where entropy is decreasing, like the construction of your own body, there's going to have to be very exothermic reactions associated with that to make the reaction occur spontaneously or naturally. The word your book uses instead of natural again is spontaneous, right? Spontaneous, what occurs on its own. So that tells us whether a reaction will occur or not, but it doesn't tell us a lot about how fast that reaction will occur. So some reactions are spontaneous and occur very quickly. For example, when you light a piece of paper on fire, that thing is just going to light up and react very quickly. Or if you light a stick of dynamite, that's going to be a very quick reaction that makes an explosion. Um, but then, and so those reactions are obviously spontaneous and they're very fast as well. But there are spontaneous reactions that are also very slow. For example, if you leave, a car out in a field, um, it's going to eventually rust. Will it rust today or tomorrow or next week? Maybe not. But if you give it a long enough time, it will eventually rust. The rusting is spontaneous, but the speed is pretty slow. So, what kind of factors are going to decide how quickly a reaction will occur, if it will occur? So first you decide, will it occur by itself or not? Is it spontaneous or not? And if you decide it is spontaneous and it will happen on its own, then, well, how fast will it happen? And that depends on several factors. One of them is the concentrations of the reactants. The more reactants you have in a smaller space, the quicker the reaction will occur. And that is because for a reaction to occur, the molecules in the reactants must bump into each other. And so the more of them you have in a smaller space, the closer they are to one another, and the more likely they are going to bump into each other at any given time. So higher concentration is going to increase the speeds of reactions, more particles in a smaller space. Um, Also, temperature will increase the reaction. So you know from the gas laws chapter that the higher the temperature, that means a faster movement of molecules, the greater the speed of the molecules, or really the greater the kinetic energy, uh, which depends on the speed will depend on the mass, right? So you have two different molecules at the same temperature. The lighter one will be moving faster, the heavier one will be moving slower, but they will have the same average kinetic energy. Anyway, basically, you can very simply think higher temperatures means molecules are moving more quickly. And the faster they're moving, the more likely they are to bump into one another at any given time. Also, when they do hit each other, the faster they're going, the more energy will be involved in that collision between the molecules. And that's going to also cause reactions to happen more quickly when the molecules slam into each other at a higher speed. Finally, the presence of a catalyst will speed up a reaction. And a catalyst is a substance that makes a reaction go faster, but is not itself a reactant. It will actually be involved in the reaction, but will not be used up in the reaction. The catalyst will still be there at the end. But because it is involved in the reaction, it does cause the reaction to go in a different way that is faster. In biology, we have lots and lots of catalysts in our body, which are actually specially formed proteins that our body creates that makes reactions go faster. And the catalysts in biology are referred to as enzymes. Enzymes is a biological catalyst. So let's break down each of these factors in terms of why it is that increasing the concentration or increasing the temperature or adding a catalyst will speed up a reaction. First of all, reactions occur because molecules collide with one another. So if you have greater concentration, those molecules are more crowded together. So in any given amount of time, they're going to collide with each other more often. Now, if you increase the temperature, you make the molecules move faster. And so this has a kind of double whammy in terms of the, uh, the effect here. Because when you make the molecules move faster by increasing the temperature, not only do they hit each other more frequently, they hit each other with a greater energy. Instead of bumping into each other lightly like this, if you increase the temperature, now they bump into each other really hard. And the greater the energy of the collision, the more likely the old bonds in the reactants are going to break and new chemical bonds will be formed. And so you will get your product. You're more likely to get your product when the molecules collide with a higher energy than when they collide with a lower energy. And so raising the temperature not only makes the molecules hit each other more frequently because they're moving faster, so they'll find each other quicker, but also when they do hit each other, they hit each other with more energy. And if they hit each other with enough energy, the reaction will be initiated and bonds will break, new bonds will be formed, and you will get your product molecule. So when it comes to catalysts, we said catalysts are molecules that speed up a reaction but are not used up when the reaction occurs. And so how does a catalyst work? Well, it works by bringing the molecules that must collide together in the same spot. So generally in an enzyme, for example, you will have one molecule that will bind to the enzyme. And then another that will hold it in place and in the right orientation. And then a new molecule will come in and be able to react with that molecule being held there in place. Also, often a catalyst will weaken the bonds. So when the first reactant molecule, so let's say you have a catalyst and it's a glob, it's shaped like this. This is the protein. And then there's a molecule that comes in here, it goes in there, and then it's just the right shape so that it's going to fit right in there. And it's exposing the molecule that needs to react. Okay, what the catalyst will be doing, it will be pulling also on the bonds. It will pull on the bonds with attractive intermolecular forces and it will weaken those bonds, and that will also help the reaction to occur. Because now if this bond right here, let's say this bond right here has now been weakened by the pulling of the enzyme on the atoms here, the attraction towards the atoms. Now, if another molecule comes by to react, that molecule will more easily react and begin to form the bond, because this bond will now be starting to break. And then the new molecule will be formed. So let's say this one goes here and you get a new molecule, and now this molecule is left here, and it will unbind from the enzyme, and now we have our new products here. So notice too that these molecules will be held in the correct orientation. The correct orientation in this one is one in which this atom here is sticking in a way so that it can begin to interact with the atom on the other molecule and begin to create a bond. Also, this bond here is breaking at the same time, and that will facilitate the reaction and make it easier to happen. So catalysts work by bringing the molecules together in the same spot, by weakening the bonds that have to be broken, and by holding the molecules in the correct orientation so that the collision will occur in a way between the two molecules that will help the reaction to occur by breaking old bonds and making new ones. So we've talked about these. I would encourage you at this point perhaps to pause the video and think about what you think the answers to these questions are. And then after that, unpause the video, and then we will discuss the answers. But give these questions a try on your own. Pause the video, and then I will explain the answers after. So pause right now. Okay, you have now thought about the answer. You've unpaused, and so let's talk about what you decided. So we talked about this chemical cold pack. You burst the seal in the chemical cold pack, and some water mixes with this solid, and it feels cold in your hand. So since it feels cold, that means the energy is going from your hand into the reaction that's occurring in the cold pack. So we would say that this reaction is endothermic because the energy is going in to the reaction. In terms of entropy, is entropy increasing or decreasing? Well, when water is getting mixed with the solid, when we mix things like the mixing of the jelly beans in your book, it's very difficult to unmix them a lot of times. This is a more disordered type of arrangement, and it takes energy to separate things that have been mixed. And so we have an increase in entropy in this reaction. And we know that we had to have an increase in entropy because we know spontaneous reactions will generally be exothermic, but if they are endothermic, that's only because the entropy is increasing so much that that makes up for the fact that heat is not being released and causing an increase in the entropy of the surroundings. So here, when things are getting cold, let's say you have your cold pack, the energy is going in. Well, the surroundings are getting cold. So cold things, that means their molecules aren't moving around as much. That's a decrease in entropy on the surroundings. So if we want this reaction to go, the entropy inside must be increasing. And the entropy is indeed increasing inside the cold pack because we are mixing things. And when we mix things, that's an increase in entropy. And the second question was, why does milk spoil faster when you leave it out of the refrigerator? And that is because the temperature is higher outside the refrigerator, so chemical reactions occur faster, and those include the kinds of reactions that are occurring in the biological reactions occurring in the small organisms, the microorganisms that are causing the spoiling of the milk. And so these reactions are occurring much faster because the molecules that have to react are moving more quickly, so they will hit each other more often. And so the more often they hit each other, the more likely a reaction. Also, when they do hit each other, they're hitting each other with more speed. And so that means with each collision, there is a greater likelihood that those molecules are colliding with enough energy to break the old bonds and to make new bonds, to create new molecules. And so the milk spoils faster when you leave it out of the fridge. It spoils much faster, right? Like if your milk is in the fridge, it will last for like 2 weeks. But if it's outside on the counter, it will barely last for like a few hours. And that just goes to show you how much temperature affects the speed of reactions. It affects it again in two ways: by increasing the likelihood of collisions because molecules are moving faster, and increasing the likelihood that that collision will result in a chemical reaction because the molecules are moving faster and collide with greater energy. And so that is the first part of the chapter here where we describe why chemical reactions occur due to increase in entropy in the universe, and also how quickly they occur and what causes them to occur more quickly. They will occur more quickly when there's a higher concentration of reactants, there's a higher temperature, and also in the presence of a catalyst. And a catalyst is a molecule that speeds up a reaction but is not used up when the reaction occurs. All right, so that's the end of our first video this week. Thank you for listening, and I'll see you in the next video, our second and final video for this week.